Right. Testing, testing. Close. So let's get started. Good morning. So today we will talk about regression, and hopefully we finish almost all. And but something we done on Wednesday we will have a lab section. So that will be almost conclude everything we have in the course, so that you can prepare for your test next, not this, but next Friday night. And then next week we will try to do some review, or depend on time. Probably I will discuss some last year exams. It's already all the question is already on the textbook, but probably I'll release the question paper also as well. But you see the same question anyway. But we can go over that if we have time. And this time after this we'll give you the last assignment. But because of I think we should have a little bit like slightly tighter deadline, because I want to release a solution before the exam. So probably I will make a deadline on Wednesday. But don't worry, there were only 2 questions. So 1 question for ANOVA, 1 question for regression. So it shouldn't be it's much shorter assignment. So it shouldn't take more than 1 hour at most. I mean, because mainly the calculation part. Okay, so it shouldn't be a big issue for you if you have been looking at that. So to facilitate your review or review next week, I also released the document here. Is if you go to the Blackboard, you should be able to see this one. This is all the topic that we cover in this semester. Okay, so you can see the first page of review, and the remaining page will be all the thing. Probably we'll do it on Monday a little bit, review a little bit, and then we go over the past year exam. And then maybe the very last class, we will talk about something. I mean Q&A, or do some little bit more programming, because you're in the lab anyway, or just allow you to do Q&A. So it's just basically you should be able to finish everything in this week. Okay, so you can start taking revision, or that's it. Okay, so I think I have said again, right? Because some of you request, so your project can be, say, delayed for 1 week. Okay, so it would be like I think 9th, right? If I remember correctly, it's 9th of the 12th, yeah, 12th of December. So that delayed it for extended for 1 week. Okay, so you can do your exam first, and then you can just and you shouldn't spend too much time on it. Okay, because it's just considered as a work that should summarize what you learn. Okay, you are not, for individual, you should not write more than 2 pages, right? As I said. Okay, please don't write more than that. And I will not read beyond 2 pages, right, for each one. Okay. So let's very briefly review the regression. Okay. For the regression, then let's quickly review the regression, and then we should be able to almost finish everything there. Okay, today, and we'll have maybe probably some programming on Thursday. So again, what's regression? And regression is basically this trying to draw a line on a scatter plot. Okay, and the scatter plot is representing how 2 numerical variables are related, right? Say income or education, and drug dose and recovery time, so on and so forth, right? So basically, it's a 2-dimensional graph. I want to draw a line, and that line I want to be a best fit line. And what we learn is what we call least square method. It's looking at the vertical distance from the line, okay? And we take its square and sum of all points, and we try to minimize it, okay? The reason why you want to take the vertical distance is because it's experiment idea. You control as x, and you want to predict the y, okay? And you want to see how change of x affect the y. So it's a causal impact from x to y. So because you can control x, right? This experiment idea. So that's why you want to minimize for the model, you want to minimize the distance between the line and the point, because that is how accuracy your model is. And just to remind you that this is the slope intercept form, right? Is y equal to alpha plus beta x, right? Is the slope intercept form. And the formula is this one, I minimize the square distance, okay? And what we have here is the formula for the least square method, okay? I hope you can remember this. At least you know what is how to estimate beta, right? Beta is covariance over variance. Whether you use the sample version or population version, it will work, okay? Another formula you should see is the line passing through the center. So if you plug in the mean, okay, of this, you can calculate the relay alpha and beta in this way, okay? So these are 2 facts that you should memorize. Of course, in the current exam, you know you can bring your notes, right? So that's not a big deal, but you should be able to remember this, right? You don't have to remember the derivation, the math behind, but I hope you at least know the formula, of course, and you understand what is the implication of those, right? Because remember, correlation is measuring how it related, right? So that's why you will see this, and later you will see how this regression, okay, indeed is related to the correlation coefficient, okay? Today we talk about that, okay? You understand how this related to the covariance over, so here you have beta is this guy, right? The beta hat is covariance xy over covariance x, okay? And you learn from topic 1, R is correlation coefficient is this guy, okay? And you want to ask, okay, is there any relationship between this, because it looks somewhat similar, okay? There's some way, and then this also measuring the 2 variables are correlated, right? But in that case, x and y is symmetric, right? You change it, you call x and y and x doesn't really make a difference. So you want to know if this would make a difference. Would this related to anything here? Yes, it will, okay? very soon we will see this guy will be an important thing in our model. Okay, but let's wait until later day. We'll talk about that. Okay, and so this is the example. I think we go over that last time. It's how you can derive the covariance x and y, and we show you to Excel, right? How to do slope, how to intercept, how can you from scratch you do the covariance, variance, mean, and mean to get it. Okay, so these are the important steps. Okay, so and the least square is just try to minimize the distance between the line and the point, right? But there's nothing about statistics so far. So now these 4 classical assumptions is trying to give some probability content there. As you can see, these 4 assumptions, why we need these 4? Because this would lead us to what we call the Gauss-Markov theorem. And before I go back to the assumption, so let's see what these 4 assumptions brings us. Okay, the advantage is we will tell you the least square coefficient. Okay, is actually a good thing. It's called unbiased estimator. Okay, in the sense that they're accurating things in a good way, such that you on average you get what you want. Okay, and also the efficient estimator, in a sense, is the lowest efficient variance. Okay, among all linear estimator. Okay, but anyway, it means that they're good and they're accurate. Okay, that's the thing in your mind is the least square estimate, accurate and good estimate, unbiased and accurate. Okay, so then go back to the assumption here very quickly. So the first one means that x and y are related linearly. Okay, you have to assume, if you want that to be a good model, you have to assume that how the data is being generated. Okay, as you change x, okay, there's unknown constant alpha and beta. Okay, such that whenever you have x, you have times the unknown constant beta and unknown constant alpha. Okay, and they are all constant. Okay, what is not constant is the epsilon I. Okay, epsilon I is the error, and plus the error I have a yi. So that means that even though everything is the first 2 components fixed, okay, the last component is not fixed. So that's why you don't see all the point on the same line, right? Because it depends on error, it may go up or go down the line. But on average, it is going to be 0. Okay, so that's why it's a good as a model where have same x, you can have say this scatter plot, right? It can be above or below the line because of the epsilon I is error. And you may ask, what is error? Again, error is something that we didn't model within this framework, which means that there's something is not there yet, or something we ignore, or something we don't have measurement. For example, if you try to explain y is the income and x is the number of years the schooling, so what is missing in this model? Maybe epsilon I, maybe your EQ, maybe your social network, maybe even your luck. Okay, so so that is the missing thing there. And for the classical case, we assume xi are in the not random. Okay, so basically you can imagine that you at the experiment, you control in the lab. Okay, and 3, the random term have 0 variance. I guess that's not a big deal because you have alpha. So if non-zero, you can put it in the alpha. I think the most important restriction here is we assume that the error have the same variance for all observation. Okay, so but we have been having this for say ANOVA, right? ANOVA, we assume same variance for each observation. So it's not a too big a deal. And if you study further, you notice we can relax that one. Okay, this one is easy to relax. Okay, and it wouldn't affect our estimate, least square estimate. Okay, alpha and beta same. The only thing you will see different is the later is the formula for inference and hypothesis testing will be different if you realize that, but overall everything will be the same. So that's not an important restriction, okay? And errors are not correlated with each other, okay? So this is the model where you consider financial data that will be problematic, right? Because you imagine each observation each day, okay? And you know day by day errors can be correlated, right? Because you can imagine that if yesterday the stock market is going up, it's more likely that today go up than go down, okay? There's a trend there, right? If yesterday is going down, it's more likely to go down and go up, right? So then this is how it fails. So that's why when you study time series econometrics or time series study, look at the times data, that will be problematic, right? Because if yesterday you're happy, you tend to be more happier today, because there's some temporal relationship between different observations, okay? And similarly, this one would be the same idea in the financial data, right? Because when the market is calm, the variance is more. When there is a financial crisis, right, the market up and down more quickly, okay? So these are some of the reasons why this model you have to study further, okay? And as I said, this is the very useful model to discover the causal relation, right? But anyway, as I mentioned many already, so just go back to here is talk about the model, right? How do you interpret this, right? So you would be beta is the coefficient, slope coefficient, and it means if x increased by 1, y will increase to be expected to be increased by beta, right? If x increased by 2, y will be expected to increase by 2y, so and so forth, right? And what is alpha? Alpha will be the value of y, or so be expected value of y if x is small, right? So do remember, here I should forget to say how average of y, not just y, but average of y, because you didn't talk about the error, right? So, but anyway, it doesn't mean that, but you know what I'm saying. So, do note that the interpretation have to be not causal because you just run regression, okay? Unless you know from the beginning x is something you control, okay? Or you know the reason that x is actually causing y, then you say causality. By running the regression, doesn't bring you causality, okay? You need to have some extra model, extra reasoning to say x cause y, right? Just like you have physics, you have some theory, x cause y, or there's cause and effect, you can see temporal thing, right? You push the thing and then it fall down, then you know, okay? So, and another thing to remind is you are explaining how the variation of y by variation of x. So that means that in this model, if you subtract y by its own mean and x by its own mean, the model is the same, okay? The reason why is this is because of the way we draw the graph, right? Remember, this is x, this is y. We have a bunch of data point here, okay? And you know when we try to do the best fit line, right? It will be, we're doing the following, right? We are looking at the mean of x, look at all the coordinate. We figure out, look at x, only the x, right? What is x bar, right? Remember x bar is what? You just calculate all the x, the mean of x, okay? So look at x, right? And also the same, you'll be doing all the same for the y, okay? Y bar, right? Which is all y coordinates, okay, of the observation, and the best fit line, right, will be passing through the center here, okay? So that means that instead of thinking the origin is here, you will draw the same line if your origin is here. You move the coordinate center from here to here, okay? You have the same thing. So that's why you have to change the model from y to x to y minus y by x minus x bar, same thing, okay? So just shift the thing in the from one direction to the other, the same thing. Okay. So now we'll talk about the error a little bit more. Is because this can help us to do inference. Okay. And you remember the model. Go back to here. The model. What remain in this model is unknown. There are three parameters in this model. One is alpha, one is beta, the other is sigma. Okay, alpha, beta, and sigma. The three things. And we know the least square actually gives us alpha and beta. Okay, so least square only gives alpha and beta. But if we have the classical model, we have one more thing to do, sigma. Okay, and what sigma brings us is how the error term looks like, right? So how error is this model, right? You can easily see even from this model is if the bigger the sigma, okay, the worse the model, right? If the sigma is very small, the model is very good. So sigma is one way to see how good is the model, right? Because you have one line, you can have the data can be very near the line or very scattered out, okay? So one way to measure is the sigma. Of course, we'll give a better measure. Later you will see, okay? We'll be related to this measure here. But you can see sigma is also a good measure, right? Because sigma is measuring how the variance error, okay? It's looking at how good the model. So we want to estimate that. And sigma is nothing but just the error term, okay? So how do you estimate the variance of the error term, right? So first you to estimate the error first, okay? Error is the vertical distance, right? Is this minus the line or other way around, doesn't really matter, okay? It's y minus yi hat, right? This y hat, okay? Is this guy, right? This is yi hat, right? And this particular point maybe is called x I, right? And yi also minus hat, right? Is the epsilon I, okay? And then what are you going to do, okay? Is to look at, you never observe epsilon I, you never ever observe alpha and beta, okay? But you are able to see, you can ever to calculate alpha hat and beta hat, okay? You can use the same formula to estimate the epsilon I, okay? Because the underlying true thing is alpha and beta, okay? But depend on what data you draw, okay? Actually depend on what relation epsilon, okay? You will have different alpha hat and beta hat, okay? But in that case, we can still estimate epsilon I, okay? And remember the variance of epsilon I, okay, is sigma square, right? Variance of epsilon I is sigma square, okay? It doesn't depend on I, okay? So we really want to say, you use this, okay, to estimate to be a sample variance, okay? So, and the sample variance, right, is measured by this minus the mean, and I didn't write it here, but you should see, not difficultly, this guy, the mean is 0. Mean of the error is 0, right? Because you are making sure that this is up and down will be the same, then you should expect the residual, the mean of the residual is 0, okay? So that's why how you have this minus 0 square, so the 0 is gone, so there's only this one left, right? And you will see we will divide by n minus 2. You are asked why n minus 2 here, okay? The reason is same as what we remember the formula here. In the topic 1, we have this, right? Okay, and we explained it in our topic 4, why n minus 1, because of the reason is mainly this guy is being estimated. right? If we know mu, we actually don't need it, but we use x bar instead of mu, so we need to be n minus 1, right? If you look at the proof, that would be the reason why you have this, because of the variation actually less, because you know, if you fix the n data point, right? If you estimate sample mean there, if you fixed n minus 1 point there, the last one you know, because you already fixed the sample mean. So the variation is 1 less. Okay, that is the reason why we explain why it is there, right? Because you estimate this guy, okay, so the variation is less. Okay, so that's why you can only divide a smaller one. Same here, y minus 2 here, because you estimate two things, which is fix the alpha and beta. Okay, you have to calculate alpha and beta. In that sense, you will actually have less variation. Okay, you fix two number. Okay, and of course the reason why is this, we can prove it, right? Because this is unbiased estimator. But of course, I don't want to go to do the proof, but you can just say this is the reason why is the same as the idea there, right? It's unbiased estimator. Okay, that's why degree you divide by n minus 2 there. Okay. So this is the standard error of estimate or standard error of regression. Okay. So this is S is same this guy. So this guy will be super useful. Okay, we'll be using this for our hypothesis testing and estimation. So this will be the key variable to do the calculation. So that's why we go to the example to show you how you do calculation. Okay. So this is X and Y. Okay. This is example. We can calculate Y hat. How to calculate Y hat, right? Just go back to the beginning here. The Y hat is just, right? It's here Y hat, right? It's just the alpha hat plus beta xi. Okay. So we have alpha is 3.9, beta is 0.7. Okay. So it means that how to get the column of Y hat will be the first will be just remember alpha hat is 3.9, beta hat is 0.7. Okay. So how to get the 4.6, right? Is 1 multiplied by 0.7 plus 3.9. 3.9 plus 0.7 is 4.6. Okay. So on for every calculation, you get the yi hat. Okay. And then subtract the first column from the the third column, you get this one, right? This subtract this one, this minus this one. Okay. So you got all the epsilon I. Okay. You got the epsilon I, right? And then you got the equation. The formula is square each element plus together, right? And divided by 5 minus 2, right? Is here. Right? It's here the formula. Formula S in this framework, not in the regression, right? It will be very similar to this one, right? But it will just epsilon I hat square and minus 2, because this guy is 0. Just to remind you, the error, okay, or the residual mean of residual is 0. So that's why you can cancel this out, okay? And minus 2 because you estimate alpha and beta. Okay. So what you get is 4.367 and take a square root on both sides, so you got something like 2. So this is you will see this will be an important measure we're using today. Okay. So this will be key, and you should know how to do it. And later you will see this Excel function to calculate directly. Okay. Here, although I show you this, Excel is called STEYX. Can calculate this. Okay. We will show you afterward. Okay. So that would be the important thing here. So now, I guess since we learned so many hypothesis testing and estimation, it will be useful to go a little bit further, right? So, and we have good point estimate for alpha and beta, which is this alpha head and beta head, right? Because they're good as the point estimator, okay? But the thing is, there are two things we want to go more is, can we do interval estimation for alpha and beta first? Second, is alpha and beta are meaningful? Is it different from zero? Okay. The important thing is, okay, if we care about the alpha, the intercept and the slope, right? We want to see whether it's zero or not, right? Suppose you want to claim this is positive slope, right? We want to check if beta is actually zero or not, or alpha is zero or not, right? So that would be the thing we care, okay, or equal to a certain number as well. So how do we do it? Okay, and the first thing is we don't want to show it here, but we can actually show the how the alpha is related to the sigma. Okay, the reason go back to here is the equation. I have the alpha here, and I can have maybe I have alpha here, right? Alpha hat is coming from y bar minus beta hat x bar, okay? And x your control is independent, right? Is something you can fix, okay? It's not random. And y is x plus epsilon, right? So this part is a random part, right? This depends on the epsilon I, okay? And beta is also depend on epsilon I because beta is, remember, is y, the formula will be x minus xi bar and y minus y bar and sum of x minus x bar square, okay? X, maybe just put I here too, okay? So these are constant. These change according to the epsilon, okay? So these are based on epsilon, okay? So the variance of alpha will be related to the epsilon I, okay? Which is sigma. So that's why you see this formula there, okay? Looks complicated, but the proof is rather simple, but I'm not going to do the proof, but you can easily check the proof is 1 page, 2 page of proof, okay? So, but I'm not going to go over that, okay? The proof, okay? But try to see what's the meaning of this, okay? Look at the denominator, okay? Denominator is actually somewhat similar to the variance, right? It's the deviation is how each observation is different from the mean. Okay. So if the variance is larger, okay, that means that the variance is actually getting a smaller. Okay. In why that's the case, okay? If the deviance is larger, okay, actually means the data are more spread out from here. Okay, so it means that you have more data here and there. Okay, that means that the line will be less likely to wiggle, right? So that's why you have this idea here, right? If this is very small, that means that the data is very concentrated on here, right? The x is all around this guy, and you want to try to estimate this intercept, then will not be very accurate, right? Suppose this is very far away, right? X bar is very far away, imagine, right? And that means that if you are very far away and the data is very concentrated on the mean of x, is far away from 0, then you do not really accurate, right? So that is the idea. And of course, the sigma is larger, then it's larger, right? When n is larger, then everything keep constant, then you should be able to get more accurate. So that's why I have this formula, okay? But I'm not going to go to detail or to explain why, because no one actually remember this formula anyway, okay? Just that you try to convince you this is the right formula, That's what I'm trying to do. Okay. And of course, if your x is bigger, then everything will become bigger anyway. Anyway, now the key here is this one doesn't depend on anything about assumption on epsilon I. Okay. So now if you remember when we try to do interval estimate, we need to make some assumption, right? Either we have to use central limit theorem to say sample is large and normal, or we have to assume the distribution underlying is normal. Okay, so we'll do the second round here is we assume the error are normal. Okay, do note that we already have the mean of the error term is 0, the variance sigma squared. The extra assumption here we make is normal. Okay, the bell curve. Okay, what does that mean? The bell curve actually means the following, right? It means that for every point you have a something called bell graph here. Okay, so the mean is here, but the error can go up and down. Okay, so that is the main idea here. If you every point have the same bell graph here. Okay, and in that case, we know this coefficient, intercept coefficient, also follow a normal distribution. Okay, and in that case, because normal, we can do standard Z test if we know sigma, which we don't know. So that's why we will be relying on estimate this guy. That's we have to use T. Okay, so that's why when we replace sigma square or actually sigma by the S, okay, the square root of everything, put sigma by S. S is coming from S square coming from this one. Okay, and this will be the standard error. Okay, and what does that mean? It means that the following is a very simple idea. You learned it from the t-test. Okay, if you want to test whether alpha is equal to A or not, you have this over the denominator. That is Tn minus 2. Okay, well, n minus 2, the same idea. You have n minus 2 here. Okay, because we estimate two coefficient, so that's why n minus 2. Okay, so let's also see the next is, as we said, we estimate the mean. Okay, so this test statistics, okay, if you convert, will be same as the confidence interval, right? So with the denominator, sorry, the numerator, denominator, critical value. Okay, let me repeat. Okay, you estimate the mean, right? Remember t-test. Okay, if you have a t-test here, okay, if this is, you can just ignore the 0. The confidence interval will be this guy, plus minus the critical value, and then denominator, right? This is the same we have been doing since the beginning, right? So this is a good point estimator, as we mentioned already, right? So that is actually this kind of here, right? And we know the margin of error is like this guy, right? Just the denominator times the critical value, right? So that means this is the coefficient. Is there any question? Okay, but let's see the example. So again, we have this, right? We know the alpha and the beta. So what's the goal? First thing is we want to check, okay, whether alpha head is different from 0 or not, right? So we know that actually, I don't know whether you can see this, but let me erase this one. Okay. So we want to test whether this is different from 0 or not. Under or now. Okay. We know if epsilon I follow normal, this guy, this, okay, what looks like normal if you know the sigma, but if we know, then we'll change to T. Okay. So that is what we're doing. Okay. And the alpha we have is 3.9. Okay. The question is supposed to do the two-tailed test. We want to see this area times 2. Is it bigger than alpha or not? Okay. Of course, because we know this going to be t, then we go back to here. Right? We're going to convert this to here. Okay. And how do you convert this? Right? This over the standard error. This guy. Okay. So just calculate standard error first. So look at the formula. What's the error? Standard error. The denominator is this funny guy. Okay. This funny guy. Don't worry. You never remember. You don't need to remember anyway. You see Excel calculate that for you. Okay. So, but you need to see only this is from the S here and sum of this square and I anyway. It's a very crazy thing. Okay. Maybe not funny guy, it's crazy guy. Okay. But don't worry. Excel is very easy to calculate. Okay. And we learned that from the previous steps. Okay. How do you calculate this? Is very simple. This is just 1 square plus 2 square plus 3 square plus 4 square plus 5 square, right? Each 1 square. Okay. And this one is not difficult. It's just like the mean is 3, x bar is 3. So for each observation you minus 3, so 1 minus 3 square, 2 minus 3 square, 4 minus 3 square, 5 minus 3 square, add together is equal to 10. Okay. So then it's simple. We have this guy s, this guy square root of n is 5. Okay, this is n, and this is 10 is sxx, right? It's this guy. Okay, so that's how you get this expression there. And once of this, like, is 2.19, so it's here. You just basically this gives you this 2.19. Okay, and what you remain is look, you know how to do it, right? Just the right tail. Okay, and the times 2, right? So just look at here. Okay, look that you need to calculate is the t 1 minus t dist 2.19. Okay, and degree of freedom is n is 5, 5 minus 2 is 3. Okay, so what we need is 1 minus, make it bigger. 1 minus equal to 1 minus t this. Okay, 2.19. Okay, degree of freedom is 3 because 5 minus 2, true. Okay, this is the right tail only. Okay, so we need to multiply by 2 to get the two tail. Okay, because we are doing two tail here because we want to test the hypothesis whether it is different from 0 or not. That is standard thing to do. So multiply 2. Okay, so this is unfortunately 11. Okay, so 11 means you can't reject it. Okay, so which means that we cannot say with 5% significance level that alpha is different from 0 or not. Okay, so that means that although we found the intercept is large, 3.9, indeed we cannot exclude the case under 5% significance level that is different from 0. Okay, so which means that the co-intercept is basically useless. Okay, the reason why, because we have very little data. Okay, if more data here, this should be something that we should believe. But is that okay? The next thing is to look at the critical value. Okay, critical value can be just very simple, right? You just look at this. This is T3. Okay, so we will look at T inverse. Okay, and 95%, which means that 2.5% here. Okay, so the left hand side is 97.5 is 0.975. Okay, degree of 3. Okay, so that's you get the 3.18 there. Okay, so that is how you get this one. Okay, 3.182. So this one is bigger than this value, 1.77. Oh, it's a 1.79. Sorry, not 2.9. It's 1.79. Okay, so I should change back to it's 1.779. 1.779 here. Okay, and it's even bigger, 70%. So you cannot. The p-value is way more than 5%. So you really can't reject them. Okay, and the very last we have is the confidence level. Okay, so basically this is coming from here, 3.9 is the numerator here. Okay, plus minus the critical value, which calculate already. Okay, and 2.19 is denominator. Okay, so this is how when you talk about the critical value and the confidence interval and test statistic are related in this way. Okay, as long as talk about the sample mean, that will be always this format, right? Of course, it will be different from proportion will be different. Okay, have to be careful. And F will be a little bit different, but for the same simple cases like this, right? Because this is the value, and indeed you see this value is come from -3 to 10. Okay, what does that mean? It means that 0 is included in this range. Okay, when 0 is included, it means that we cannot reject, right? Okay, so I guess let's have a break of 15 minutes. I think someone is coming to do the cost evaluation, I guess. You're doing evaluation? So someone is doing the evaluation. I will be off for 15 minutes, so you can have a break. And I'll come back like 10:30. Okay. So this time I'm not going to answer questions, but I'll come back and answer questions. So I see you.
Hello, everyone. Please follow the instructions on the screen to do the online CT questionnaire. Have you all finished the questionnaire? If you need more time, you can continue after this session till tonight. Thank you very much.
So let's have a 5 minutes break. Have to see any question. concept 呢個 random variable 嘅 estimator， 佢哋唔知道佢可能會大有細，即係啲幅放，或者咧係個 data， 但係可能你有唔同嘅 data 嗰陣時，即係隔離班玩啲網頁遊戲咧就，但係嗰啲網遊戲西方嗰啲打怪法師啊。我不唔大學校，我大學係 A 班，真係真係。 Okay, so let's resume. So just to remind you that what we talked about today is our estimator beta hat. Oh, sorry, not this one. So we just, before the break, we talked about this one, right? We do how to do the hypothesis testing, okay, on alpha, and we need to make assumption on epsilon I, okay, follow a normal distribution like this, okay. So that means that likely the same x, like the most likely center, and we're likely on the bell on the y, okay. So and now the question would be, we can do the t-test, right, and we can do the confidence interval, okay. So that is not something very difficult to do, okay. And later you will see when Excel is just immediate, okay. So it's not something difficult to do. So now what we want to do is to do the same for the beta hat, okay. The same idea here, actually much more easier, is how the hypothesis testing on beta hat, okay. And before we do it, we don't need to do normal assumption. We just try to see what if the beta hat is, right? And the beta hat is this formula, right? And then you can calculate variance of this formula, right? Because beta is this, right? And we don't go to the math, but you can try to look at the math. It's not difficult, just one page of proof, okay? But I'm not going to go to the detail. But actually the math is rather elementary. Just basically just use our standard variance formula can derive it, okay? So for those who are interested, you can try to look at it. It's not something terribly complicated, but if you are, don't worry, just like this formula, right? But anyway, just go back to here. Sorry. Okay, this is the formula, and you further assume it's a normal, okay? Then the beta hat will also be normal. In that case, we have this also very similar to this one, right? Now it's not alpha hat, but become beta. Okay, we do the t-test, and we do the confidence interval. So we can see what we learned from the last chapter directly translate to this chapter. So there's nothing very new here, okay? Except you may ask how to derive this formula. And as I said, this year, we're not doing anything about formula, so we just skip, okay? Because some of you already said this is already very complicated, okay? So I don't want to further complicate you. So sorry if you are very math inclined, we just skip. But I think if you're math inclined, there's no problem to read this. It's not something, there's nothing very deep here, okay? There's no particular formula. Just applying the standard formula there, okay? And if you replace sigma by s squared, you take a square root, you go from here to here, okay? Replace sigma because we don't know the s, right? And then put it there. This is the square root of that, okay? Because that's how you do the t-test, right? So that's how you do the t-test, right? At n-2. So the same thing here, okay? And you can see the estimation, right? This is the point estimate, right? And this is the margin of error, okay? So just the numerator, the denominator, and critical value, okay, of the two-tailed test, okay? And of course, I here, same as we do the two sample thing, we just consider the two-tailed test, and sometimes you only want to see the one tail, right? So that is I didn't mention it, but you can see you can do one tail test here. I didn't mention about any. I just turned a two tail, right? You can have a one tail, but the test is the same thing here. Okay. So let's try to see this. Okay. So this one is easier. From last question, we'll calculate S and SXX, right? So basically just this divided by this guy. Okay. And once we know this, just like let me change this thing, right? Just 0.666, right? Then will be 0.7. This beta over this SE is 1.59. So look at this diagram again. Instead of alpha, we have beta. Okay. So what we have in this is we have beta head here. Under the null is a 0. Okay. And what we have beta head in the data is 0.7. Okay. So the data here is 0.7. Okay. So we want to see this area multiplied by 2 because 2 tell test. Okay. Is it bigger than alpha or less than alpha? And we use alpha to be 5%. And although when we know sigma is a bell shape, right? Because we know sigma, then we have this guy, right? Okay. But since we don't know, we use a t, right? So it'll be t to the n minus 2. 5 minus 2 is 3. Okay. And how you convert the t is the what you observe over the standard error, and standard error we calculate is 0.6608. So this 0.7 over 0.608. So that what you get is 1.059. Want to know this area, and we know this area, right, is going to be look at the t, basically the same thing. You replace 1.779, right, to 1.095. Okay, so that's the same formula here, but instead of this, you have okay, is 1.095. Okay, because this calculate the left hand side. Okay, 1 minus calculate right hand side because 2 tell multiplied by 2. Okay, so you can calculate the p-value. Even without calculating, you know it's going to be more than 5%, right? Because at least 5% is 1.96, right? At least 2. Okay. For the z is always 2. For t is must be greater than 2, right? Because t is much fatter. Okay. So we'll be much further away. Okay. So, and the critical value will remain unchanged regardless of what you're doing, right? So that means that your number is 1.9. The critical value is 3. So it's not more than that. Okay. So we can't reject. Okay. So even though with beta head is 0.7, we can't really say that where beta is 0. Okay. So that means that even though we do all the work to calculate beta, this beta doesn't tell us anything meaningful. Okay. So that means that if you really want to say something in your model, okay, you need to make sure that beta is different from 0 in order for the model to be somewhat useful, right? Because if beta you cannot tell it's different from 0, then this model is unlikely to be trustable. Okay, so you really don't want to use it. Okay, this is the most important step when you do regression, to make sure that your coefficient is different from 0. Otherwise, your regression is not useful. Okay, and when you do your project, remember if you do regression, you have to check that. Okay, and you can also try to look at the interval estimate of beta. It's just the value plus minus critical value. It should be 2 if the critical value should be 2 here, but anyway, multiplied by this guy. Okay, and this gives you the value between negative 1.4 and positive 2.8. So 0 is included. Okay, so that's an issue there. Okay, so okay, actually there should be, remember this is 2 here, right? So just to remind you, there's a typo. Should be 2. 3.182. Okay. Doing same. Yeah, this is correct, the previous one, but I think I have typo here. This is 3.182. Okay, so that would be you get the hypotesting for alpha and beta. Is there any question? Okay. If no, then let us continue to do one more test. Okay. We learned the t-test and z-test. There one more test we learned in the last class. Okay. It's called the f-test. Okay. Or the ANOVA, right? So is it ANOVA to be applicable here? Okay. Turn out to be yes. Okay. Actually, we can do ANOVA to test the beta. Okay. So we'll use the t-test here. There's another way to do it. It's called the f-test ANOVA. Okay. But before we do ANOVA, I want to do the same thing as we do the sum of square and mean square, and you will see first how these things are actually related to what we call the R, as I promised at the beginning of the class. Okay. So first is the following. Okay. Consider the following thing. Okay. Is we remember the analysis of variance is comparing different variants, right? We're comparing the variance between group mean and variance within group. Okay. If variance between group mean is too large, they can't have the same variance. Okay. So we will use the similar idea here. Okay. First is we have a linear model. Okay. And we want to see if the beta is 0 or not. Okay. The question would be, you want to use x to explain y. Okay. So if x is not useful, what you're going to use for prediction? It's just y bar. Right? Suppose you want to predict y. Okay. If x is not useful at all, okay, actually you use y bar here, right? And that means actually if you exogenously fix this 0, okay, what you predict yi hat is just y bar, which is just alpha hat, just yi hat, right? Because this is, if you want to predict average the income, okay, if you think education is not useful, what is the average what is the income you predict is just the mean of the mean income, right? Average income is the best thing to predict. If you randomly pick up a guy, what's the income, right? If education is not a useful thing, okay? Let me repeat the statement. You're going to meet a guy, okay? He tells you his income and his number of years in school, okay? If the model is useful, you can use this equation, get the alpha and beta, and predict what is y, right? But you know that if education is not useful, okay, how are you going to do that? What's the best estimate? We'll be using the average income in the population to predict what is the randomly drawn next guy's income, right? So that means that if beta hat is 0, this guy is 0, okay, the best thing you can do estimation is exactly this y bar. Okay, so that is something that we know. Okay, and actually the yi minus y bar is the power of the model, right? Because this is what the model explains. Okay, which means that for, say, for this particular x here, okay, so for this my model here, okay, this is something we want to explain in total. Okay, this point to here, okay, you take square, add everything up, this is called SST. Okay, this is the, for each point, the vertical distance between the point and the mean is called SST, some of them, of course. Okay, and this is the first thing. The second It's rather simple. It's the thing you explain. It's the line to the center. It's called SSR. Okay, which is the part that explained by your linear line. Okay, that's why you have this is the line is the y hat minus the y part. Okay, the last one is yi hat minus y. Okay, which is, remember this guy is actually epsilon, right? So this is SSE. Okay, so that's why SST is you do some math, we don't prove here. SST is sum of SSR plus SSE. Okay, there's some math here why this is true, because they're square. Without square, it holds true, right? But with square, it's not immediate why they're true. Okay, but turn out they're true. Okay, there's some complicated math behind. Actually, not complicated, but it's just like I think one slide. Okay, you can see one slide. You can prove this is the same. Okay, but we don't do the proof, so that's why we try to claim this is true. Okay, look at the graph. Is the point to the mean will be same. We'll explain SST, right? We want to explain how this data different from the mean, right? And SSR is a line to the mean, and SSE is from the observation to the dot to the line. Okay, and square the sum of all this. Actually, you have the identity. Sum of square total is decomposed in two parts. Okay, basically, it's the thing you want to explain can be decomposed to the model explain the part you didn't. Okay, so in that case, you can calculate the ratio, right? The ratio is SSR of SST is the part you have explained it, okay, and part the total variation. Okay, then that is actually the fraction of the variation explained by your model, right? And then you would imagine this part, this fraction is a fraction, right? Because SST is bigger than SSR, right? So this must be, this measure must be between 0 and 1. Okay, because SST is equal to SSR plus SSE, right? Because this, so this must be between 0 and 1. And of course, you will see the bigger this number, the better, right? If the number is equal to 1, that means that everything is on the same line, right? If this is 0, that means that this is basically a horizontal line. Okay, so you can see it should be very familiar. It's very similar to this one, right? Because if everything on the same line, R is either 1 or -1, right? If it's a flat line, you know, R is going to be 0. Okay, so it's natural to ask how they're related. Okay, turn out to be, very interestingly, this one square is exactly this guy, this fraction. So let me repeat. The coefficient of variation, you take square, is exactly this fraction, right? Because this fraction is between 0 and 1. This fraction is between -1 to 1. Okay, so turn out to be the correlation coefficient square is actually R squared. Okay, it's very surprising result, and you will see the bigger the R square, of course, the bigger, right? Because they're fitting better. And this is how we call, actually, this is called the goodness of fit, okay, of the model is R squared. Okay, later you will see when we run regression, you will see this measure. Okay, is there any question? Now, if you're happy with this one, Then we'll tell you the very simple thing is we will do F test ANOVA. Okay. So far we just give you R square. So one more thing is we do ANOVA. Okay. So what we are doing here is also same idea, comparing the variance. Okay. Do remember, just remember the ANOVA, right? Just to draw it again. The ANOVA. I think now it's okay. I can erase this guy. Right? Just remember one-way ANOVA. What's the intuition of one-way ANOVA? Just to repeat here is you have possibly different data set, right? And this will be the data given by the mean of group 1, right? This is the mean of group 2. ANOVA is measuring this, right? The variation within the group, which is called MSW. And you calculate, this is overall mean, you calculate this variance. This is called the MSG. And you compare MSG and MSW. If MSG is too large, they can't belong, it can't be true because they should have different group mean. Okay, so the same idea goes on here. Okay, we want to see if beta is 0 or not. Okay, if beta is 0, then SSR, or divided by the degree of freedom, is called MSR. MSR should be small, right? Because MSR is the variation explained by the model, right? If this guy is small, okay, compared to this guy, okay, then beta should be 0, right? If this one is very big, right, then this cannot be, beta cannot be 0. Let me repeat the argument again because I think this is important. Okay, you can calculate the variation of this, right? The SSR, right? For each point. For each data point, right? You can calculate the SSR, right? Or this SSR, right? And average of those is called MSR. Okay. And you want to look at the variance of all this. Okay. All this. Okay, look at this point here. Okay. And sorry, yes. With this one for this guy. Okay. All this thing. Okay. And you want to compare all the mean, okay, to the line, right? So all this, okay, compare to the point to the line, okay. And if beta is 0, okay, this should be very small, okay. And if beta is non-zero, there is much flipper. This guy must be big relative to this guy. Okay, so that's why the F test will be you divide this over this. Let me repeat the statement again. Maybe I draw it again. I draw another line because it come clumsy. Let me do it again. So you have 9 here, okay, and you have this, okay. Look at the point here, the data here, this to here. This is the amount explained by your regression. This is called SSR. Okay. The average of those give you the MSR anyway. Okay. And this is called SSE. Average of those is called MSE anyway. So this is all they are also measuring the variance. Okay. And what you want is you want to see if beta is equal to 0 or not. Okay. If beta actually equal to 0, then on average, what you can explain should be also should be very small, right? This guy should be very small, right? So because this line should be very flat, right? Because if beta is 0, and the true thing, you many joy of saying this one would be very flat. Okay, because your model can't explain the thing. When you want the regression to be close to this horizontal line. Okay, so this should be 0. But this guy, the error, is independent of what beta is, right? Because always the sigma, right? Because this error is dependent on how the error is being drawn. It's independent of the model. So this should be, if under the null hypothesis beta is 0, this is very small compared to this one. If beta is not 0, this line will be, this will be much bigger, right? So this will be bigger than this. So that's why we have a one-tail F test. Okay, so that is the F test here. The MSR over MSE. Okay, let me repeat the idea here is, if the beta is not 0, that means that this, the proportion explained must be way bigger than not explained, right? Because if the portion explained should be much flatter, either in this way or the other way around, right? Because you can explain it's either this or this, right? If the model can't explain, then your beta will be very close to flat one. Okay, imagine the real one is very flat, right? This guy is very small compared to this. You see the idea here. So I hope that I convince you that why you have MSR over MSE but not other way around. Okay. And degree of freedom is 1 over n minus 2. Okay. And probably you ask why I divide by 1 here. The 1 here is exactly the reason is you only have 1 coefficient. Okay. So that's why just 1, right? Because the only coefficient is beta. Okay, so that's why only 1 group. Okay, so ANOVA with 2 groups, right? So that's why that's the case. Anyway, so that is how this looks like. Okay, so you can calculate the y high, x I, y hat. I told you how to do y hat. And okay, y hat minus yi. Okay, this is, you subtract the third column from the first column, you get our data there, and you can calculate y my hat, and same as y hat. Okay, and okay, this is the SSR, right? This is the SST. This is the SSE. Okay. Just sum of the square of all this, right? Because this is something I want to explain. SST. This is amount you explain. Sorry, this is amount. This is the amount you explain. This is SST. SST. This is the. Sorry, this is SSR, SST, SSE. Okay, SSE, SST, SSR. Okay. And then you can calculate the MSR. Okay, just this over 1 MSE, the same, and you can do the F test. Okay, the F test is same, just MSR, MSE. You calculate this and go F, and you can notice the interesting thing here. I want to highlight again is the when you take the T statistics, you square, you got the F. Okay, this is very special thing about linear regression is if you do the T statistics, okay, for beta, okay, this is coming from the last example, 1.905. Okay, if you go back to here, this guy, actually you square, surprisingly, they give you the F here. Okay, you square this guy, give you this guy. Okay, so that means they actually give the same, and you can actually check the p-value of this will be the same. Okay. Now I know it's too many information. I'm going to end here. So that's why we do Excel. Okay. We're not going to the last two things there, but I'm not going to push forward. Let me do the Excel then to make sure that you don't feel too tired. Okay. So what I'm going to do is to copy the data from the test. Okay. We actually want to show you how you can calculate wear strain. Okay. So this is the Excel. Okay. What I want to show you is how you can do the several things. How you calculate R square. Okay. How you calculate the standard error regression, and then we tell you how to do add in. Okay. First, we call how we do the slope intercept. Okay. Slope and intercept. Okay. That's very simple. Let me do the formula test here. Okay. This is coming from the last class already. Just slope. Okay. And then you put Y and then you put X there. Okay. So again, this one I'll upload on the Blackboard. Okay. So this is the slope. Okay. And the intercept is like this. Right. Intercept is all the Y and all the X. Okay. So that would be the slope intercept, right? So that's the same as we expect already, right? So we know it. Okay. And we know last time how to do covariance over variance to calculate the same thing. Okay. I'm not going to repeat that. So what I'm going to do today is going to show you the two things. Is they call standard error of regression. It's called SDEYX. And the other one is called the R square. Okay. So we have standard error of regression. Okay. What's this? This is the S. I erase it, but that guy. Okay, you calculate this guy. What you will see is 2.08. What is that guy? This guy is the, remember, go back to here. I have said the important thing is S. Okay, because S up here, here is 2.09, right? And S up here in FE denominator here. Okay, and we show you how to calculate S is this 2.09. Of course, you can go all the way up, but this is how you calculate S. Okay. And second one, I want to show you how to do the RSQ. Is what? RSQ. R square. Maybe I do RSQ the same. RSQ is R square. Okay. R square is this Y and this X. Okay. It's 27%. Okay. That means 27% of the thing I want to explain is there. So it's the same as this guy. Okay. Now I want to show you the formula I mentioned is here. I want to prove this is right. Okay. The coefficient of variation, coefficient of correlation, square give you this guy. Okay. So I hope you still remember this guy is CORR. Right? COREL. Okay. COREL. Okay. Doesn't matter you put X and Y first because its time is independent. Oh, I missed the R. Okay. Now they're not the same, right? But you take the square of it. Okay, so you can see this number and this number the same. So that's we have proof. Okay, I mean proof, verify the R square is exactly the small r square. Okay, so that's why the big R square is actually the small r square. Okay, that's why the coefficient of determination is the square of the correlation coefficient. Okay, so that two things here. Now, the last thing I want to show today is trying to show you can use Excel add-in to calculate almost everything we say in the class. Okay, that's one. So how basically we can show you that is very quickly. So again, we go to the file because the data had not been there yet. So go to file, option, add in, and go and the NS2 pack. I think from that at this moment shouldn't be any difficulty for you for this one. So let me show you the regression. And in the regression, we have everything there. Okay, data analysis. You go to regression here. Okay, regression. Okay, and tell them what's the y, what's the x. Okay, so y will be the y here, right? And the x will be the x here. Okay, once you have that, because the data have label at the beginning, so we take the labels. Okay, and then you're almost done. Output range, you decide where to output. Let me decide what about here. Maybe here. Maybe just this here. Okay, and then okay. And then we just make it smaller. Oh, sorry. Okay. Now what we have is the regression result. Okay. First thing is you can see here, the 3.9 is here. We can see it. The 3.9 is here, and 0.7 is here. So that is exactly what we have here. Maybe I change some color to make sure you see it. Okay. And actually, the standard error automatically for you, this is SE alpha and SE beta. Okay, 2.19 and 0.06. Let me go back to the slide and show you there. Right? SC alpha, the intercept is 2.191. So it's here, this guy. Okay. And this is 0.6606. So 0.660 is intercept error. So it's SE beta. Okay, this guy. 0.6608. Okay, it's there. And then the T-stat 1.7 and 1.05. Again, it's very simple. It's there, right? 1.059. The T for the beta. And the T for the alpha is also 1.779. It's here. Okay. So you can see everything we said in the class is here. Okay. And you can do the p-value. Okay. It's two-sided p-value. I already told you how to do this, right? It's the T inverse thing. So it's, this one. Okay. And also you have 95% confidence. That is same as what we have here. Okay. I don't know why they have a 295, but this is the 95, right? 1.4 and 2.8 is exactly what we have shown. This is the alpha, right? 3.7 and 10. So that's there. Okay. So basically everything here, everything in the bottom table, the most important thing we have explained. Okay. Everything here we know how to do. Okay. And the next is R square, the first table. R square, we have here already. So it's there. Okay. The R square is there. The R square is here. And the next thing is the standard error. Standard error, STYX is over there. The number cell D4, right? It's this guy. Right, let me use some color there. They're the same thing. Okay. Now what is left is this guy. This guy is just SSR, SST, right? This is the SSR, this is SST, this is SSE. Okay, so you can check with my slide, right? How do we get 4.9? Right? 4.9, 13.1, and 18. So it's all there. Okay. And then you degree of freedom is 1. This residual is n minus 2 is 3. So this over this give you this give you this over this. And this over this give you this one. And use F test to give you this one. So you should be able to do everything. If you understand, except there's some just R square and multiple R. Only 2 things is not, these 2 things you will not cover, okay? But other than these 2, okay, you know everything. Okay, so you know everything from the XLR. Okay, so I guess I should end here. We will finish the rest in the Wednesday. So I will try to give you. I will release the homework, which will be due on next end of Tuesday, because Wednesday we'll post the solution before the class. Okay, so don't worry, just 2 questions. Okay, so you should be able to do it. One ANOVA, one regression. With this, you should be able to answer most questions. Anyway, okay, I will see you next time. I will see you on the computer lab.